So this is joint work with Noam, Nisan. The K-cutting model is the following. We have a resource that is the unit, that can be modeled as the unit interval. So you can think of it as a piece of land, and we'll have a set of interested parties or players, and there will be n of them. And each person will have some preference over the resource, and this will be represented through a value density function that is non-atomic. And so, for example, if we want to figure out what is player one's value for an interval, we will take the integral of this value density, and that will represent his value. So this model can be seen as the limit of taking a discrete model where there are atoms and making that go to infinity. And the goal will usually be to find an allocation, which will mean a partition of the cake so that each player receives a piece that doesn't overlap with anybody else's. And we will also try to allocate the whole cake. And moreover, we usually like to be fair in some way. So there are various notions of fairness. So there's proportionality, which says that each player should get their minimum fair share. So without loss of generality in this model, we can normalize. So if you get the whole cake, your value is 1. So this minimum share will be 1 over n. A stronger notion will be requiring envy freeness, which means that you would not like to take somebody else's pieces. You would like your own at least as much. There is also equitability, which says that the players are equally happy with their piece. So you could think of this as being relevant in situations of conflict where you don't want the other player to be happier than you are with your own piece. And perfect, which basically combines some of these and says that the value of each player for every piece is 1 over n. And a simple example of a protocol is cut and choose, where we have 2 players. And let's say we ask one of them, Alice, to cut the cake in half according to her evaluation. And then we ask Bob to take his favorite piece. And you can see that here the valuations are different. So Alice likes the cake equally, while Bob is more interested in the right hand. So cut and choose guarantees that the allocation is proportional and be free, but only for 2 players. In general, we can think of how can the players achieve a fair allocation, given that everybody knows only their own, they start by knowing their own value. So you could think of having a center or a mediator interacting with the players and asking them information until the mediator extracts enough information, or you could also just have the players talk among themselves. And there is a standard query model that has been used to study query complexity in K-cutting, and it has 2 queries. So it has a cut query where you ask some player a cut of some value v. So then the player has to report a point where their value for the piece from 0 to x, where x is the point, is exactly v. And an eval query where you ask a player, what's your value for this piece? In an example, we ask Alice, in cut and choose, we ask Alice to report the point that is half for her, and then we ask Bob to evaluate it, and we give him the larger piece. Of course, there is one issue with this model, which is that it has infinite precision, so this is hard to implement on a computer. But perhaps another issue is that it's not clear by this model, so we could think of other kinds of queries. We could think of how is your value for the interval AB larger than some C? You could think of various other things, like is the number in the representation at some bit equal to whatever it is. A further issue is that there are also protocols that have not been exactly formalized in terms of what exactly is the model there, and they are known as moving knife procedures. So we will try to study these in a unified way using the strongest possible model, which is the communication complexity model, which is studied a lot starting with Yao. And here we will allow any Boolean query that depends on a single valuation. So basically each player will start by knowing its own valuation, and then they will exchange bits according to some protocol, and the communication complexity will be the number of bits that they exchange, but we'll take the worst case. So there has been related work in K-cutting in particular on complexity, and especially on query complexity. There are also some lower bounds and upper bounds. So to be able to talk about communication complexity, one thing that we'll have to do is that we'll have to relax the fairness notions within epsilon. So we will be happy with proportionality in the sense that each player gets 1 over n minus epsilon of their value, and then the freeness within epsilon and so on. And this is in fact necessary because it might be the case that the valuations are a little strange, and maybe the only cut point is at some irrational point. Another aspect of the model that is important when studying communication is that the input valuations should have bounded density, Otherwise, the problem becomes meaningless. And the reason intuitively is that the players might have a very tall interval, like very small but very tall, and all their value is essentially concentrated there. So then to get there, we'll have to exchange a lot of bits. And then we will also require that the number of cuts produced by the allocation is bounded. And I'll explain why this is. But intuitively, if you have lots, if you can chop up the cake in as many pieces as you like, then you might as well do that beforehand. And there are, in fact, it is sometimes relevant to have a piece that is connected, for example, a piece of line that doesn't have holes in it. So formally, the deterministic communication complexity of some fairness notion F will be the number of bits sent on the worst case input required to compute F fair allocations. And we'll have a similar definition for randomized communication complexity, but there will have some probability of succeeding. And we'll take the error probability over the random choices. Okay, so I see there is some. Yeah, that's supposed to say remarks, but so usually one interesting aspect about this problem is that the existence of fair solutions is usually proved via some fixed point theorem. So this is true for any freeness, for instance. There it's proved via Stirner's lemma. Perfect allocations are proved using Borsuk-Ulam fixed point. And so this work can also be seen as studying the communication complexity of fixed point proofs. And another observation is that non-deterministically, all these fairness notions have logarithmic communication complexity. And the reason is that if a player could guess kind of the right points, then that would not be very expensive to communicate. And there are not many problems known where there is an exponential gap between the deterministic and non-deterministic complexity, with Nash being an example. So we established formally that without density bounds, which I mentioned before, then the problem is basically not meaningful. You can't do anything. So basically, the height of the evaluation shows up in the lower bound. So for the purpose of this talk, I'm going to assume that the height is fixed. It's arbitrary but fixed. And also, if we don't bound the number of cuts at all, then what we can do is we can chop up the cake into like 1 over epsilon squared cells, and then we allocate each of them uniformly at random. And this will, with high probability, be very nice and almost perfect. I mentioned that there is a class of protocols that are moving knife protocols, and actually these protocols can be used to find some of the fairness solutions that have fixed point proofs. So we give a formal definition, but to say it informally, so basically we'll have a collection of knives that move on the cake. They're held by different players or by a referee, and there is some stopping condition point at which you find your fair solution, hopefully. And the proof is usually via the intermediate value theorem for moving knife procedures. And this is a simple example of Austin's procedure for computing perfect allocation. So remember, a perfect allocation is one where each player gets 1 over n. So for 2 players, this will mean each player gets exactly a half. And for this, you might need 2 cuts, in fact. So the way we do this is that we have a referee that starts at the left part of the cake, and then we ask Alice, let's say, player 1, to hold her knife at a point so that the value of the cake between the knives is exactly half to her. And then we ask Bob what's his opinion of this piece. So if Bob says it's also half, then we are happy. If he says that it's more than a half, then it means that his value for the remainder is strictly less than a half. So it means there will exist a point in between where his value is a half if the referee and Alice move their knives continuously. And basically, we can kind of simulate the movement of the referee knife using binary search. So this will be informally a theorem saying that fair moving knife protocols can be simulated with all log square bits of communications. We'll have log epsilon for 1 over epsilon for the number of knife positions, and then a log for communication position. And basically, it will be like binary search. And an interesting open question here would be to show that there is some fairness notion that requires more higher communication, more than log square of epsilon. So this would, in particular, show that no moving knife procedure can compute it. So we classify the fairness notions that at least the most known ones, into 3 classes, easy, medium, and hard. So the easy ones will be those fairness notions that have correspond to discrete protocols. So in the Robertson web query model, that can be solved with a constant number of rounds of a log of 1 over epsilon bits. And an example of such protocols are for computing contiguous proportional allocations. So this is for any number of players, where the number is, however, fixed. And then free allocations, but with possibly disconnected pieces also for any number of players. The medium class will have moving knife protocols. So, and we'll look at contiguous and free for 3 players, equitable for 2 players, and perfect with 2 cuts. And the hard class will have everything else, and we have some candidate problems there, and then a very general upper bound. So for the easy class, basically we can get an upper bound by simulating existing Robertson web protocols. And for the lower bound, proportionality alone, in fact, requires a log of 1 over epsilon. For the medium class, we will study a problem that captures most of these problems, captures their essence, and we'll give reductions to it, and then we'll study this problem in more detail. And we'll call this a crossing problem. And one observation is that if you look at the total communication for the medium class, it looks like it is as if it is the same for the easy one. But the difference is that the moving knife protocols will require many rounds, which is not true for the easy problems. Those can be solved with a constant number of rounds. So the crossing problem, which we define, is the following. We have 2 players, Alice and Bob. Alice gets a sequence x0, x1 to xm of some numbers. And those numbers, let's say, are chosen from the set 0, 1 to m. And Bob also gets a sequence y0 to ym. And all we know about these numbers is that initially, if we look at the 0 index, x0 is less than or equal to y0. And at index m, the order is flipped, so xm is greater or equal to ym. So this means that there is a point where the order flips. There is some index I, so that at I, we have xi is less than or equal to yy, and the opposite at I plus 1. And there is also a monotone variant of this problem where we moreover know that the sequences are sorted. So we know that Alice's sequence is increasing and Bob's sequence is decreasing. So, sorry, I messed up I don't know, the slide is not showing. So that's supposed to show that monotone crossing is equivalent to equitable. So we give reductions both ways between monotone crossing and equitable. So to remind you, equitable for 2 players with connected pieces. So we want to find a point x star so that the value of player 1 for the p0 x star is equal to the value of player 2 for x star 1. And the idea, so for one direction, which will be useful for getting a lower bound, is that to go from equitable to crossing, if you have a k instance, you can set the index xi to be the value of Alice, for example, for the piece from 0 to I over m. And for Bob, for his value for the interval I over m to 1. Then crossing, so this will be equivalent to this. You really can't see this. I'm sorry. So this is perfect. And so here again, we want 2 cuts, and we want 2 points x star, y star, so that the value between them is a half. And here the observation is that there is a connection. The second point is related to the first point. So we can, in fact, also see it as a kind of like a 1-parameter problem. So we will choose xi so that the value of Alice of player 1 for the interval I over m to xi is half, roughly. We'll get it roughly half. And for Bob, it will be similar. And then we'll find a crossing point, and that will correspond to the perfect allocation. And then monotone crossing is, in fact, it's harder than in the freeness. So here the reduction captures one way. So if we can solve monotone crossing, we can also solve the freeness. So this is with freeness with connected pieces. So an upper bound for crossing is, so we can solve this basically with log square m deterministically. And we can do a bit better with randomization. And the reason is because we can ask queries of the form xi is less than yi. And the randomized communication complexity of this is in fact a bit better. So we can do this with log m. So we get log n times log m. And monotone crossing can, in fact, be solved more efficiently. Here we'll introduce a slightly more specialized version of the problem where the numbers are chosen from the sets from 0 to k, and we'll get the deterministic communication complexity is log m plus log k. So when k is equal to m, we'll get log m. So to talk a little bit about lower bounds for crossing, which will be useful for getting lower bounds for some notions of fairness. So we'll think about rounds, basically. So I said that moving our protocols seem to have the feature that we need many rounds. So we'll think of the players communicating in R rounds, let's say each requiring, each allowing t bits per round. So now if we simulate general Robertson-Webb protocols, then we can do this in a constant number of rounds and with log of 1/epsilon bits per round. A lower bound is that the monotone crossing problem requires log m over log t rounds of at most t bits each. So if we, so for t is like for log of 1/epsilon, we get like log epsilon over log epsilon. And the proof sketches to use a round elimination technique, which was introduced by Milterson, Nisan, Safra, and Wigderson in '95 and improved by Sen and Venkatesh in '08. So basically, the idea is that if we have some communication problem f and some parameter k, then we will look at a problem that is expanded where Alice has, in fact, k strings, x1 to xk, and Bob has only one string, y, but he also has a pointer z, which is an index. And the goal of the player will be to compute the f of x, z, and y. So basically, Bob is pointing to one of the strings that he's interested in. And the round elimination lemma will say that if Alice goes first, then they're not going to do very well. So because she doesn't know which string is interesting to Bob. And the lemma makes this formal. So if you have a protocol with Alice going first with t bits per round in R rounds for solving pk with some probability delta, then you can actually do it in one less round with slightly higher error probability. So we are going to use this, and the way we'll use it is that, first of all, the pk of monotone crossing can be reduced without any communication to a monotone crossing. So basically, if Alice has a bunch of these instances, she can stitch them together, making them taller and taller to make only one instance from them, and she can do this without any communication. And then to put everything together, we'll use induction. So basically, for the base case, we'll do it directly, invoking the lemma. And then we'll assume there is some R-round protocol with some p and error probability, and then we'll infer what we can do in one less round, and we'll get a contradiction if that is too good. So for 0 rounds, we have constant error. Okay, so we studied the communication complexity of fair division notions. One of the main open questions is to get a super logarithmic lower bound for some fairness notion. So some natural candidates are contiguous and free allocations for n greater or equal to 4 players. So this proof actually requires proving is done via Sperner's lemma, and moreover, for 3 players, it's like Sperner's lemma on the line, which is like the intermediate value theorem. For 4 players, the proof looks more like search on the grid, basically. So this is a candidate for kind of an intuitive reason for why it might be hard. And it would also be interesting to have a lower bound that is super constant in terms of the number of rounds for 3 players. And this would also be interesting to understand the joint dependence on n and epsilon. So this is a table with upper bounds obtained by simulating various existing protocols. So thank you.